This conference will now be recorded.
All right, everybody. Thank you for joining us for the Satellite Book Club seminar series. This is session number 86. Hope everybody's doing well. Busy weather day. Thanks for taking time out of your day to be with us. Today's presentation, development and applications of multi-satellite water vapor products for forecasters. We're joined by John Forsythe and Sheldon Kusselson, both associated with CIRA. Just a few reminders before we get started that this session is being recorded. There will be an opportunity for Q&A after the presentation. We're particularly interested in questions from our field offices and regional headquarters. Please post your questions in the chat room and we will field them that way. Or if you have a longer comment, please indicate as such and we can certainly allow you to speak to the group. Also, if you are joining from a group account or an office account, if you are asking a question, we request that you please use your full name or specify your full name when asking a question in the chat so that we can get back to you if we need to do so. We are also looking for future presenters, so if you have an application that you'd like to share with members of the field, we'd love to have you be part of the Satellite Book Club as we head towards session number 100 this summer. The training team can help create training materials that may be unavailable. Brian Mata, the Office of the Chief Learning Officer, can help with that. I'd just like to call attention to a special event next Tuesday. Many of us are excited about the prospective launch of GOES-T on Tuesday, March 1st at 4:38 p.m. Eastern Time is when the 2-hour launch window will open. And hopefully the GOES-T satellite will launch on a Atlas V rocket from Kennedy Space Center in Cape Canaveral, Florida. That coverage will begin at 4 p.m. Eastern Time on NASA TV, and GOES-T will become GOES-18 once it reaches geostationary orbit. More information will be coming from the TowerS team on Tuesday regarding new GOES rocket plume RGBs, which capture rocket launches and other hotspot signatures. If you want to watch the launch from GOES-16, please note that these RGBs are only available for offices that have upgraded to TowerS RPM version 22. So once again, we are 5 days, 4 hours, and 32 minutes away from hopefully a successful launch of GOES-T, which will become GOES-West. I'd like to thank the TowerS team, particularly Kashad Bowman, the Office of the Chief Learning Officer, the GOES-R and JPSS program for their support of the Satellite Book Club. Without further ado, let me introduce both John and Sheldon, starting with John Forsythe, who received his master's in atmospheric science from Colorado State University. He supported and led remote sensing projects for NOAA, NASA, DoD, and the private sector, with emphasis on infrared and microwave remote sensing of water vapor and clouds for weather and climate applications. He's joined by Sheldon Kusselson, working part-time as a research associate at CIRA, supporting new satellite products for forecasters. You may know Sheldon retired in 2015 after working 36 years with the NESDIS Satellite Analysis Branch, providing operational satellite moisture and precipitation analyses, as well as short-term forecast guidance in support of the National Weather Service. We value both their perspectives and welcome to the book club. And Sheldon, welcome back.
Thank you. Thank you.
Okay. Thank you, Jordan. So I'm going to talk just briefly about the status of these products. One that's transitioning to operations, one that's been operational, and then I'll hand it over to Sheldon for some forecast examples. So kind of the statement of the problem, these are microwave driven products mostly. We do use some GOES and GPS data in the TPW product, but microwave sensors have historically, or still are, only available on low Earth orbiting satellites, which can be difficult for forecasters to use due to the data gaps and the coverage. So they're hugely important to assimilate into the weather forecast models. And they have the ability to tell what's happening under the clouds with water vapor profiling capability. So the solution to sort of make these more friendly and usable in the forecast environment are these blended multi-sensor satellite products with advection from the wind. And just one question I'll toss out there is, so these are being assimilated into the models. We try to keep these products sort of pure from not having a model dependency. So in other words, it's retrievals that are based on the microwave data without a dynamic weather forecast model. So as developers, we're always thinking of that. You know, how is this better than the model? Do we capture cases where the model might miss things due to its assimilation? So so that's something that, from the field we might you know, like feedback on about that. Just the big picture, TPW is increasing about 1.5% per decade. This is a study from about 30 years of microwave data, the SSMI sensor. So over the Gulf of Mexico in the past 30 years in the summer, roughly about a 6% increase in total precipitable water on average. So the blended TPW product's been operational since 2009. Really capturing water vapor, which is the fuel which drives these heavy rain events. So both these products that Sheldon will go in more detail, the blended TPW and the Advected Layer Precipitable Water, ALPW, I like to say they allow forecasters to view the plumbing of the atmosphere. So if you think of these atmospheric rivers as pipes of water vapor, you know, how wide is the pipe, how fast is it flowing, that kind of thing. And as I said, they're both model independent, which allows that comparison to models. And just the ALPW, we've been able to distribute it out in AWIPs over the past 5 years or so, initially with some help from NASA's support. Just a quote there from the Tucson office that it's really useful, like for the Southwest monsoon season. And then the Weather Prediction Center has been a heavy adopter of this and has really given us good feedback through this through that JPSS proving ground process. And here's an example where they're looking at a situation with a channel of moisture coming up through the central plains and increasing the flood threat. So I said WPC is a heavy user. This is during the monsoon season. You can imagine this day pretty busy with, as I said, kind of looking at those pipelines of water vapor as they flow in and support flooding. So just a little bit on the status. The blended TPW became operational in 2009, and since then we've added a changing cast of spacecraft to it. So what's going on now are enhancements to this product that'll become operational in probably about the spring of 2023. And these are the first real science algorithm upgrades in about 10 years. So some key points, we'll be using GOES east and west in the clear skies. That's proven to be performing very well, both in our own validation and testbed participation and evaluation by forecasters. And then right now, the blended TPW does not advect the low Earth orbiting data, so it kind of stays there. So we'll use this mimic technique that Sims and Tony Wimmers have developed to move that around. And then sort of a better handling of the GPS data over the CONUS. GPS is really valuable because even in precipitation or heavy precipitation, it still performs the same. So, so that's an important addition that we have over the CONUS. So then on the ALPW side, that will also become operational in early 2023. And in the interim, Sierra is producing this hourly in AWIPS 2, and right now it's going to about 27 WFOs and NHC and WPC. So back to this point about the models versus model independent versus not. This is just an outline of that MIRS microwave retrieval system, which is sort of the backbone of our products because it produces water vapor profiles, and then that can be integrated in to get total water vapor using the spectral data around 183 gigahertz. That's kind of the key key area that gives you the profile information. The lower frequency, the 23 gigahertz, helps with the total column. So the retrieval itself does not have a dynamic forecast model dependency, but like I said, we use model winds to advect things. We use the GFS winds, and just thinking further out, there's been some demonstrations of small sats, kind of cheap, inexpensive, cheap radiometers that carry these 183 gigahertz channels. So that might be something to look for over the next, I guess I would say 10 years. Maybe we'll have some different spacecraft. And the reason I mention that is because this is the type of diagram I always like to show. It's a clock. The polar orbiting satellites are sun synchronous, and this shows so that means they come over at the same local time every day, so at 12 hours apart. So this is our current configuration for the Advected Layer Precipitable Water. There's 6 satellites, but you can see that there's sort of periods of high coverage, and then these 4, 5, 6 hour data gaps. So the advection portion moves the data around, and it sort of makes it appear to a forecaster that it's a geostationary microwave instrument, which of course we've never had. So it kind of makes it appear as if they pass over every hour. Then on the blended TPW side, these are the inputs to it. The upper left is the mimic TPW. The center top is the GOES east and west, and you can see this was a case where there was some of that loop heat pipe issue, which we've learned enough about to filter out. And obviously, as Jordan said, we'll be looking to a new GOES West spacecraft hopefully very soon. And then the GPS network on the upper right, which sort of its irregular distribution, but very, very valuable where we have it. So, and then the new product down here on the lower left. So, so that should be upgrading the operational blended TPW in this next spring. And I have a website listed there where we produce this every hour if you want to see it. And then on the ALPW side, I know probably a lot of you have seen this. Dan Bykos and Sheldon and Ed Zoke have done a lot of training, but we have online training for that product that forecasters have used through the Visit program. So, so be aware of that. And Dan and Sheldon in particular are always capturing new cases and really diving into our understanding of this. Here's a few papers we have going back to the initial start with NASA sport team, mainly about heavy precipitation, a little bit on elevated mixed layers. But I think as the developer, the potential applications to severe weather and winter weather, I think we're still really learning what we can do with the ALPW there. So that's something we continue to look in. We just actually we're communicating with the Cleveland WFO about lake effect events, and they're looking at the product specifically for that. So just for my portion, before I hand it over to Sheldon, the message is here. These operationally driven data sets really show the plumbing, as I say, of the atmosphere. And the TPW is increasing over most parts of the ocean globally. And I think, as everyone knows, there's more extreme precipitation events that we hear of. So these new operational products will be available in early 2023. And right now, under the JPSS Proving Ground, we're working on the historical context, some of the climatology from these, and also water vapor transport. So maybe if we come back to the SBC in a year or so, maybe whenever that is, we would have some new results on that. And then, of course, Sheldon has so many application examples, even way beyond what he'll be able to show today. So he always likes to keep in communication with forecasters. So then I just threw this out, sort of philosophical question. And this is a satellite book club, so maybe the answer is stacked, but will we get to a point where only model water vapor fields are needed? So with that, I'm going to turn it over to Sheldon and let him show some examples of case applications of the products. Thanks.
All right. John. SEER's Advected Layer Precipitable Water, which continues to be supported by NOAA's JPSS Proving Ground and Risk Reduction Initiative, is being prepared to become an operational, hourly derived global satellite precipitate moisture product in 2023. In the past several years, applications have been developed for the ALPW product. These applications span different hazardous weather events, such as severe weather that can result in tornadoes and strong damaging winds. Also heavy precipitation that can result in catastrophic flooding and mudslides, and also excessive cold season snow and ice. The following cases presented are a small sample of how it can help improve the analysis and forecasting of these hazardous, many times catastrophic events. Let's start with severe weather forecasting and the elevated mix layer. Tracking the EML is a crucial part of severe forecast process. In addition to the GOES-R 7.3 micron band and RAOP soundings, polar orbiting microwave satellites used in the construction of the ALPW product allow for the improved monitoring and tracking of the EML, primarily at the 700 to 500 layer. Furthermore, high amounts of low-level moisture are a necessary ingredient for severe weather forecasting. The ALPW product provides that necessary information in both the low and high layers. Here are two severe weather cases from different type storms. On the left, the remains of Hurricane Isaias that was lifting north from North Carolina to New Jersey in August of 2020. A narrow band of relatively low moisture at the 700 to 500 layer was aligned with very high moisture in the lowest layers of the ALPW product. This satellite signature helped produce the most tornadoes ever from an East Coast landfalling tropical cyclone. To the right, a middle of the country 2019 severe event featuring the same EML and low-level high moisture advection signature that helped produce tornadoes and damaging winds from Oklahoma to Illinois. Let's next turn to heavy precipitation analysis and forecast with the ALPW product. Knowing the moisture content, origins of that moisture, and how that moisture is transported at various layers of the atmosphere is an important aspect of heavy precipitation forecasting that can result in flooding and mudslides any time of the year, like seen with the top cases, and catastrophic snow and ice storms during the cooler seasons, like seen with the bottom cases. Polar orbiting microwave satellites used to produce the ALPW product allow for the improved monitoring and tracking of these events. Meteorological features such as atmospheric rivers, moisture origins, transport and convergence, alignment of the moisture at two or more layers, and the contribution of moisture above the 700 millibar layer can mean the difference between an ordinary heavy precipitation event and seen here these four extraordinary heavy precipitation cases with catastrophic consequences. Also easily seen in all these cases is the moisture advection connection to at least the subtropics, not just at the lowest layers, but the two highest layers as well. Now here's the test. What do all these cases, 8 of them, I know I'm missing a few, since July of last year have in common? If you mentioned atmospheric rivers for all of them, you'd be right. As a matter of fact, with these ALPW images, all had atmospheric rivers at all 4 layers. What else do they all have? Moisture transport. They all have long fetch moisture transport, not just at 1 or 2 layers, but all 4 layers. All have converging moisture transport for at least 1 layer, and many at multiple layers. Many even have converging moisture at different layers. And lastly, fill in the blank. All these cases have at least 1 layer's moisture with origins from, yes, the subtropics or the tropics. You've got the ALPW product and imagery, the meteorological variables that can be overlaid on them to confirm in your mind that the result will not just be a heavy precipitation, but an increased potential for a catastrophic heavy precipitation event. Now let's look at a few of these cases. Why did the remains of Hurricane Ida cause such prolific heavy rain amounts around the New York City area on the evening of September 1st? A few reasons can be found when analyzing the Sierra Advected Layer Precipitable Water product as early as the morning of September 1st. Multiple streams of moisture and advection of that moisture at 4 layers could be seen organizing over the eastern third of the country and just off the Atlantic coast. In addition, a moist boundary on the ALPW product could be seen from the northwest Atlantic to the New Jersey, southeast New York area at 3 ALPW layers. By the early evening, those multiple streams of moisture and their transport had come together in low layers along with a single moisture stream in both higher layers. This helped produce the extraordinary amount of rain during the evening of September 1st, near where the moist boundary at the low and middle layers was interacting with the various converging moisture streams at multiple layers. An extraordinary 18 millimeters of precipitable water was above the 700 millibar layer on top of the 42 millimeters of precipitable water from the surface to 700, making for a very deep layer of moisture. Forecasters can use hourly ALPW products in their AWIPs or on the internet to monitor these moisture developments that can lead to extraordinary heavy precipitation events, like what happened centered on New York City on the evening of September 1st. This slide was sent to Dave Riddell, the SOO of the New York City Weather Forecast Office, so he and his forecasters could better understand the ingredients that helped cause this catastrophic flood event. Comparing excessive precipitation from the past with similar types of satellite imagery and analysis can be helpful to forecasters for the future recognition of these types of catastrophic precipitation events. Using the ALPW product, we at Sierra hope to look into the moisture and moisture transport climatologies of these types of events for different seasons and parts of the country as the year goes on. I try to emphasize to forecasters that the analysis, especially satellite analysis, is an important ingredient in making a good forecast. This event was associated with the first big atmospheric river of moisture event of the season to hit California. Great feedback was provided by Warren Blyer, the SOO of the National Weather Service Monterey Weather Forecast Office. Usually the first or second heavy precipitation event of the season does not cause much problems because the dry ground from the lack of rain the previous 7 months. But in this case, the second event of the season did cause problems. And my next slide will tell you why. Yes, it had been dry the past 7 months in most of northern and central California. Wildfires had plagued a number of areas. There was an initial atmospheric river to affect the area of California on October 21st, 22nd. Then a second, bigger one coming right on its heels 2 days later produced higher precipitation amounts as seen in the previous slide. And the effect of the 7 months of little precipitation and fires prior to October 21st helped further heighten the flash flood mudslide potential with the second system, especially in the burn scar areas. The ALPW product also does well in providing an early warning signal to forecasters that unusual weather is coming their way. Already early on Christmas Day last year, the ALPW imagery and analysis of moisture advection was seeing the pattern set up for an extraordinary transport of tropical-like air and moisture to Alaska. An atmospheric river of moisture originating at the latitude of Hawaii was being transported toward Alaska at all 4 layers of the ALPW product. The first impulse brought the leading edge of deep moisture and, of course, snow. Remember, it's wintertime into central Alaska. The ALPW product can very graphically get the forecaster's attention to the real possibility that an extraordinary weather event can occur over the next few days. With its easy, recognizable signature, the ALPW imagery helped increase forecaster confidence in forecasting the devastating ice and extraordinary record precipitation amounts. Another extraordinary precipitation case to help teach forecasters the value of using ALPW imagery and analysis in their forecast to help with hazardous mitigation and identifying patterns that can lead to very unusual and catastrophic precipitation events. Usually, the right color enhancement for the amount of precipitable water will show an atmospheric river of moisture really well. In this case, the color enhancement on the blended TPW did not show the atmospheric river as well as the ALPW product. Why? The blended TPW would make you believe that there was only one wide but weak atmospheric river of moisture, but the Advected Layer Precipitable Water product, having more detail, showed at 3 layers, one focused main AR, atmospheric river, and another smaller one, but equally focused atmospheric river just to the east. That convergence of the smaller AR with the main one pumped in added moisture transport to western Washington and the southwestern part of Canada to help give excessive precipitation, resulting in catastrophic flooding the next 24 hours. This was the climax of a 5-day period of heavy precipitation last year in mid-November. The ALPW product is on the internet in some WFO AWIPSs, so check it out. Learn how to use and incorporate it into your operation. Please be on the lookout for 2 common modules this spring that include applications of the ALPW product for 2 different weather events. In summary, the ALPW product is an additional satellite-derived moisture tool for forecasters that will become operational in 2023. Applications of this product, along with other supplemental satellite imagery and meteorological data, will continue to help improve forecaster identification of hazardous weather events, like the ones seen in this presentation, thus increasing forecaster confidence in more quickly and accurately forecasting where and when these events will occur. Thanks for listening to our presentation.
All right. Thank you so much, John and Sheldon, for that great overview and presentation. And we do have some questions for you, but before we get into that, I realize that we are at the bottom of the hour. So I'd like to remind you, if you can stay on, please do. And please go ahead and enter your questions there in the chat, specifying your full name if you didn't sign in with that. We all are always, just like everybody these days, looking for your feedback. So if you have anything to say about how we can make the Satellite Book Club better, please let us know. And also, I want to remind you that this Satellite Book Club seminar series runs weekly, and we will be back next week, Thursday, March 3rd at 12 noon for Dan Bykos from CIRA is going to talk about severe thunderstorm applications from satellites. So we're certainly heading towards spring, and we're going to start covering some more spring topics here in the Satellite Book Club. All right, so with that said, you might have, if you need help configuring satellite products or you need more information about the Satellite Book Club, the TowerS team can help. Email addresses are there. I already mentioned the great support that Kashad Bowman, Lee Byerly, John Evans provide for the Satellite Book Club, and also to all of our field offices. So please don't hesitate to reach out to them. Okay, let's roll over to these questions now. And first question comes from Michael Davidson, who asks, can we rule out the higher TPW due to higher resolution sensors? And I think this goes back to the beginning of the presentation where John was talking about the intro to the product and some of the history of increasing TPW from a climatological perspective.
Yeah, that's a good question. That's a big problem with rain rate, especially because as you get higher spatial resolution, you resolve thunderstorms and more convective rain. But with TPW, that's not such an issue. It's a smoother field, and that particular climate record was the SSMI sensor throughout the entire period. So it maintained constant spatial resolution. That's a good question.
All right, fantastic. Scott Lindstrom, we have a question. Scott Lindstrom asked, what's the cause of the regions of no data? For example, the case that you showed from September 2021, the IDA case over central Pennsylvania in the 500 to 700 millibar layer. It's not really a gap in the orbits, and there's also some missing values in the ITCZ.
Yeah, that's a good question. So these passive microwave retrievals will work in clouds, but they accumulate more error in precipitation. You start sensing the rainfall instead of the water vapor, and the MERS retrievals have flags for that. So right now we're being very conservative, and where it's precipitating, we're not using the data. That's those gaps you see that very often in the ITCZ due to convection. So when we do the advected portion, it goes back upstream on the trajectories and looks for the parcel that fits where you're trying to analyze the water vapor, and sometimes that's a precipitating parcel, so it shows up as missing data. That's what that gap is.
Yeah, the only thing I would add would be back in the early days of microwave data, when the military was sending out their product, that they would many times blacken in or make any of the imagery where it was raining no data, and they were conservative also. Yeah, it's probably the rain you're seeing, which actually is another feature you can see in the imagery, which may be helpful to kind of look and compare where the highest precipitable water moisture may be in comparison with that rain area.
Okay, sounds good. There's a question here in the chat that I believe was answered, but Galena asked how the ALPW will be transitioned to operations, and Dave Donahue stepped in and said, yep, it'll be transitioned via NESDIS. So thanks for that additional information, and thanks for the answers to your questions so far. Once again, questions open.
The operational system that runs blended TPW now, we're just adding some modules to that, so it'll be the same software system, which really makes the transition a lot smoother.
Okay, yeah, appreciate that. Looking forward to that. Once again, feel free to get any questions that you may have into the chat, and we can certainly get those to John and Sheldon to answer. While we're waiting for maybe another question or two to come in, one of the things that we've had for a while when it comes to TPW are the percent of normal products that are based on a climatology for total precipitable water. What are some of the pros and cons of using a percent of normal type product instead of a quantitative TPW value in your experience?
Yeah, that's also an operational product that probably hasn't been updated like it should. The climatology record goes from 1988 to 99, so it needs. I showed the results that the TPW is increasing, so that needs to be updated. And I know there's other model products, GFS type products. So yeah, do you do standard deviations or percent of normal? We've found that forecasters use both, and maybe to communicate to the public, a percent of normal is easier to understand. But both of those products, or the model or the TPW anomaly side, really provide a quick look at where an event is happening, sort of where the action is. But yeah, units to use is, I think, a good question.
If I just may add, the percent of normal product kind of has its own type of applications that we developed and looked at. For example, the very sharp gradient between very moist and very dry to the west is a very good signature of enhanced severe weather, and it can be used for severe weather in that context. persistent high percent of normal moisture over a certain area as a disturbance approaches is a very good indicator of possibly excessive precipitation coming away. So it has a few other applications that can help enhance a forecaster's experience looking at it, in addition to the TPW product.
Okay, thank you. We got a question that came in here from Joseph Patton asking, is there an archive of the ALPW imagery that can be used for other case studies out there?
Yeah, the answer is yes. Over the CONUS, at least adjacent areas, it's changed through time as we've expanded the domain. And when it's operational, all the data will go to NCEI to be the official archive. But at Sierra, we have a sort of a unofficial archive. So the easiest way to get that is just send me an email, and I'll see what we have in our archives. Some of it's online too, but not all of it.
Okay, perfect. And once again, that email address is right there on the slide if you need it. So feel free to reach out to John. I don't see any other questions coming in, so maybe I'll just ask, excuse me, one closing question for Sheldon. Sheldon, you've had a very long career doing these types of analyses, and you've now been keeping busy in retirement, kind of continuing this work. Any thoughts of the big changes in the field over the past 5 to 10 years, and what you see coming up in terms of things we'll be able to do as far as sensing total precipitable water and working towards more accurate precipitation forecasts?
Well, some of the things that I would like to see is some of these products, the ALPW blended TPW product, be included in the machine learning, artificial intelligence, and even keeping a good archive, so that in addition, so that forecasters can go back to previous heavy, maybe catastrophic events and see how they compare with today's ALPW product or blended and coming Advected TPW product. I think that would be helpful for forecasters to be able to have a good archive to look at for a past event that they know in their particular area, to just compare events. Many pretty much similar to what forecasters may do now in trying to look at the weather patterns, surface analysis, or different things from a past event that may look similar to an event going on today, that type of thing.
Okay, thank you so much. John or Sheldon, any last comments to wrap it up?
No, I'm excited because I've been looking at ALPW product for 10, 11 years. Gave it a kudos even back 11 years ago when we were going for a NASA grant, and I'm glad that it's going to become an operational product in 2023 for forecasters.
Yeah, and thanks to Sheldon, he keeps all of us on our toes with his expert analysis, and does a real asset to have working in retirement. So really appreciate Sheldon's work.
Thank you, John.
All right, well, John and Sheldon, thank you so much for being with us today for this great presentation. As a reminder, any colleagues that might have missed it, this will be posted on through the VLab, and I'm sure that they can always reach out to John and Sheldon to get in touch if they have any questions about TPW and this work. So once again, please keep the GOES-T launch near the front of your mind if you're interested in that. Next Tuesday, March 1st, starting at 4 p.m. on NASA TV, you'll be able to catch that. And then, of course, be here. Please join us next week, Thursday, March 3rd, as we continue our Satellite Book Club seminar series with Dan Bykos on talking about severe thunderstorm applications from satellite. As always, reach out to our Tower S team if they can help you. And with that, please stay well. Thanks for being with us today and take care.
Okay, thank you.